Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Module 026, Multiplexing Techniques. Please follow me in the engineering lecture series by subscribing to my YouTube channel, https://youtube.com/@Ndinechi Michael C. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can also listen to my other lectures, more especially the ones on basic concepts of electronic communications, part 1 and part 2. You can also listen to my earlier lectures on digital communications on Module 17. You can also listen to my earlier lectures on sampling and pulse code modulation. They will all help you to understand this better. So, what is multiplexing? Multiplexing is the technique used in sending of a number of separate signals together over a common communication channel without interfering with each other. It can be observed that most of the individual communication devices require lesser bandwidth than the bandwidth of the medium connecting them. The process of making the most effective use of the channel, therefore, divides the communication channel into several numbers of logical channels, allotting each one for different message, signal, or data stream to be transferred. The device that does multiplexing is called a multiplexer, and in short, as a MUX, M-U-X. So anytime you see MUX, know that it's an abbreviation for multiplexers, and you know that anytime you hear multiplexers or MUX, it means a system of combining so many different channels, different signals, so that they can be transmitted along one channel. Now, most common use of multiplexing is in long-haul communications using coaxial cables, microwave links, and optical fiber technology. So, when we say long-haul, most of the time, you can use your computer to communicate another computer nearby or within a vicinity. But if you are going to transmit for a long distance where you will have repeaters along the line, before you get to the destination, you call such long haul communication. So that is the meaning of long haul. The reverse process of extracting the number of channels from one multiplexed channel at the receiver is known as demultiplexing, and the device used in achieving this is called a demux. So demux is a short form of demultiplexer. Now, look at Fig 1, say the basic concept of multiplexing. You see to your left where we have a mux or a multiplexer, you see channels or signals 1, 2, up to n. Now, you see that the blue block showing that the left end of that blue block is longer than the right end of that block. So just a depiction that 1 to n comes and converges into one transmission channel. To the right, you see the demultiplexer or the mux, which have a block left side shorter than the right side, showing that at that point, the demultiplexer expands the thing back to from 1 to n. So it is like, a generally accepted symbol that you draw a mux like that and draw a demux like that. So even if you see such in a circuit diagram without being told, you know that this is referring to a multiplexer, while this is referring to a demultiplexer. So what are the types of multiplexing techniques available to us? We say that there are mainly two types of multiplexing techniques that are in use. And that is, it can come in form of analog or in form of digital. Fig 2 we'll be seeing gives a detailed categorization of multiplexing. The analog multiplexing techniques involve signals which are analog in nature. They are multiplexed according to their frequency, otherwise known as frequency division multiplexing or wavelength division multiplexing, while the digital signals are multiplexed in time and known as time division multiplexing. So if you look at the fig 2, we say at the top we have multiplexing. So it can be either analog or digital. So for the analog multiplexing, it can take the form of frequency division multiplexing. It can take the form of wavelength division multiplexing. Under the digital multiplexing, it comes in form of time division multiplexing, otherwise known as the TDM. And this TDM can be a synchronous TDM. It can also be an asynchronous TDM. So quickly, we are going to look at these block diagrams one after the other. Now, we start with the analog, which is the frequency division multiplexing. So in most cases, you just see FDM. And when you see FDM, it's an accepted acronym for frequency division multiplexing. In FDM, the available bandwidth of a single physical medium is subdivided into several independent frequency channels. Independent message signals are translated into different frequency bands using modulation techniques, which are combined by linear summing circuits in the mux or in the mux block to a composite signal. In the past lectures, I've talked about modulation techniques. We talked about pulse code modulation. We talked about analog modulation. We've talked about amplitude modulation. We've talked about frequency modulation. So if you are still not getting what modulation techniques are, I refer you back to some of these lectures I've given in the past. So the resulting composite signal is then transmitted along the single channel as shown in figure 1. You've seen it, signal 1 to N multiplexed and transmitted through a single channel in figure 1. And when you put different signals together and each acting as if it is the only one in existence, that group of signals are called composite signal. Using modulation, independent message signals are translated into different frequency bands for transmission. For instance, when we were talking of sampling, we see how different frequencies appear. So those different frequencies can be transmitted simultaneously using the same channel. And what made it possible is by multiplexing them. As we go on, we see more, becomes more clearer how they are done. So the carriers used to modulate the individual message signals are called sub-carrier, as shown in figure 3. If you look at figure 3, we have source 1. Source 1 is having a frequency of F1. Source 2 is having a frequency of F2, and so on until you get to source N, which we also have a frequency Fn. So the frequencies are different. Now, if you look at source 1, which is having F1, it goes through a modulator, which modulates the signal. Likewise, source 2, source N. And all of them are summed up. If you look at where we have the summation sign, they are summed up there. When they are summed up there, they become a composite signal, and they are now transmitted through the channel. If you look at the channel, you see that we have used purple color to represent channel 1, which is having frequency F1. We have used orange color to represent channel 2, which is having frequency F2. We have used the green color to represent Fn, which is having the Fn signal. So when they are pushed to the channel from the multiplexer, what happens? At the receiving end, the signal is applied to a bank of band pass filters, which separates individual frequency channels. The band pass filter outputs are then demodulated and distributed to different output channels, as shown in figure 4. Now, it is important for us to note here, in our previous lectures, we talked about low-pass filtering. When we talk of low-pass filters, it means it passes only signals from certain point to certain point, and any frequency above that will not pass. But now we are talking of band pass filters. It means that it doesn't start from 0 to pass. It attenuates signal up to certain point and allows signal to pass, and when it gets to certain point, it attenuates the signal. So for band pass filters, it doesn't allow lower frequency signals to pass, and it doesn't allow higher frequency signals to pass. It allows only a band from this point to that point to pass. We call those filters band pass filters. We have also high pass filters. As we go on, we also meet those ones. But for now, we have met low pass filters, and we have met band pass filters. So we got to know that. So at the receiving end, you see the output, the signals we have seen in fig 3, purple, orange, and green, will come and will be, as they pass the black round circle there, the black circle there, that's at that point, which is the band pass filter. A filter that sees only F1, we take F1 to that upper output one, and only signal F1 will be allowed to get to demodulator 1. Demodulator 2 and N will not see it. Likewise, when F2 comes in, modulator 1 and modulator N and other modulators will not see it, only modulator 2, because the band pass 2 will only allow signal equivalent of F2 to pass. And like that, the whole signals will be separated at the receiving end. So if the channels are very close to one another, it leads to interchannel crosstalk, known as aliasing. When we did sampling, we talked about this aliasing. Now, this aliasing, we are calling another name, which we say is crosstalk. In communications engineering, yes, pure communications person, we know what aliasing is, but ordinary person that makes use of communication system, we see it as a crosstalk. Now, what is an example of crosstalk? You see that in TV broadcasting, aliasing, we said we make pictures to have shadow. But if we talk of voice communications, you see that at times you make a call. When you make a call, you hear other people conversing when they are talking, but they are not the people you call. That is as a result of interchannel crosstalk. Your own channel trying to connect to the person you are talking to or you want to talk to, but there is an interchannel interference from the other people, maybe already making call. Then you have what is known as crosstalk. Now, this crosstalk can come in different forms again, which we call far end crosstalk or near end crosstalk. When we'll be having our lectures on wireless communications, we'll be able to delve more into crosstalks and how interchannel interference affects it, and how to prevent the crosstalk from occurring. But at least minimize it. We may not prevent it totally, but how to minimize crosstalk. So we continue. Channels, therefore, must be separated by stripes of unused bandwidth to prevent this situation from occurring. This is one way. There are other ways. But one way is to introduce what we call the guard band. When we did sampling, we called it gap band. And why did we introduce gap band? We said to be able to low pass filter it, because we don't have ideal filter in real life, so we'll be able to have practical filter to take to filter our system. If we are looking for ideal filter, we say that we must have a sharp cutoff characteristics, which is not a practical filter. So, but here we are going forward to say that we will deliberately introduce what we call the guard band. If you look at Fig 5, you see the guard band, that there is now a separation between the purple signal and the orange signal. The essence of that is to make sure that aliasing, which is the two signals, overlapping each other, never occurred. And when they do not occur, then you can extract the purple signal without any atom of the orange signal. Therefore, your reconstruction of the purple signal will be accurate. And we say to do this, we deliberately introduce a gap, which we call the guard band. Now, look back and see how it is possible. It is possible because when we were talking of, when we were dealing with sampling, we say that it is always good to sample at a rate higher than the Nyquist rate. And immediately you do your sampling at a rate a little higher than the Nyquist rate, you'll be able to introduce this guard band. So now, say these unused channels between each successive channel are known as guard bands, as illustrated in Fig 5. So, example of a frequency division multiplexing system is the direct broadcast satellite TV. If you look at for us here, the DSTV, you see that it's only one satellite channel that brings all the signal to your home. Now you have a small decoder that now separates the channel so that you can select channel this, channel that, CNN. Those people are independent, different people that are transmitting their own channel. But the multi-choice company can acquire them and through one channel send the thing to your home and now give you a decoder which is acting as the multiplexer that it separates the signals so that any channel you click, it now gives you the signal equivalent of that channel. So that is typical example of what frequency division multiplexing does. So we have the other one, which we call the orthogonal frequency division multiplexing. Now, let's quickly look at it. The OFDM, this orthogonal frequency division multiplexing, you will not be seeing always. You will only be seeing OFDM. OFDM transmits multiple signals simultaneously over a single channel, with each signal traveling within its own unique frequency range, modulated by the data that is to be delivered. So this OFDM can come in the form of spread spectrum technique. In our future communication lectures, we will talk about this spread spectrum so that you understand it very well. But here we are just mentioning it in passing. OFDM spread spectrum technique distributes the data over a large number of carriers that are spaced apart at precise frequencies. We will see shortly. This spacing provides the orthogonality which prevents the demodulators from seeing frequencies other than the one meant for them. It is similar to FDM, but has much more spectral efficiency by spacing the subchannels much close together. Let's see. Now, so this is done by finding frequencies that are orthogonal, that is, that are perpendicular to one another in the mathematical sense, thereby allowing the spectrum of each sub-channel to overlap another one without interference. Let's bring back this home to, for us to quick understand it. What I try to do here is, well, if you look at this 6A, you will see we have 7 channels. We're having different colors: orange, light blue, purple, green, brown, sky blue, black. So channels, these 7 channels, if you transmit them using just frequency division multiplexing, you will have those guard bands, you see spaces, separating them. That will make, for you to transmit one set of these 7 signals, you will use the bandwidth from that orange to the black. Now, by applying the orthogonal frequency division multiplexing, you make your system, the one that is seeing black, to be blind to other colors. Just look at it. If we are in a class and somebody sees only blue, somebody sees only black, somebody sees only orange, and so on. If we paint something orange, it is only the person that sees orange will see it. The other ones become, the other ones will never see that. If you paint something black, it is the only person that sees only black that will see it. So we are saying that when we are able to do that, in your, what math is that? When you do the orthogonal, you see that in the mathematical sense, the signals become perpendicular. When we say that something is perpendicular in mathematics, it means that, this one is going horizontal, this one is going vertical, so there's no meeting point. When we do that orthogonal manipulation of the signals, you can now see that in Fig B, you can see how the signals come close. In the real sense, we think that aliasing or crosstalk will take place, but because one is blind to all the other colors or all the other frequencies in this case, then it doesn't see them, even if they are overlapping with the one that is seeing, provided the color is not the same with the one it is seeing. So you see that in the orthogonal frequency division multiplexing, the signals can be compressed and be transmitted using, the channel spacing for transmitting them becomes smaller. So within that point that are not being used, you can transmit other things. In other words, we say that the orthogonal frequency division multiplexing conserves channel spacing. That is, what we are saying there. So, of course, it has many advantages over just ordinary frequency division multiplexing. We say that it has high spectral efficiency, resilience to RF interference, possible to eliminate intersymbol interference, used in broadband wireless access systems, used in wireless digital radio and TV transmissions, allows design of single frequency networks, SFN, where several transmitters send signals simultaneously at the same frequency. Just like we said in your DSTV, CNN will be transmitting their own signal at their own frequency. Nat Joe Wide will be transmitting at their own frequency. NTA will be transmitting at their own frequency, but all the signals come to your house as one DSTV signal. Of course, everything with advantage must have an advantage, a disadvantage. So this OFDM has the disadvantage of being sensitive to Doppler shift. I want you to note Doppler shift when we come to talk about our radar systems. We'll be able to, explain this Doppler shift even more mathematically for it to sync very well. So we come to the next one, which is also an analog multiplexing system known as the wavelength division multiplexing, WDM. WDM is an analog multiplexing technique in which many signals of different wavelengths are transmitted in the light spectrum. It is conceptually the same as FDM, except that it operates at very high frequencies. Very narrow band of light signal from different sources are combined to make a wider band of light. At the receiver, the signals are separated with the help of the multiplexers as shown in Fig 7. So in this WDM, multiplexing and the multiplexing of light signals can be achieved with the help of a prism, which can turn different wavelengths into a single line at the output of a multiplexer and input of a demultiplexer as shown in Fig 8. Also, optical fiber communications make use of this WDM to merge different wavelengths into a single light for transmission. If you recall in your physics, you talk of how to use prism to direct your light to where you want. So we have here two figures. A is the transmitter, that is the upper one. If you look at it, we say that this system makes use of signal with different wavelengths. So you see that the first signal there starts from wavelength 1 to 2. Of course, you can convert wavelength to frequency. So it starts from wavelength 1 to 2, the other one 3 to 4, the other one wavelength 2n minus 1 to 2n. So he gets them out. At the receiving end, you see also now how they arrive. Wavelength 1 to 2, 3 to 4. Then this last one should be wavelength 2, 2n minus 1, 2n. So at the demult end, they are separated just like we said in the FDM. Now, look at how it works. For optical fiber, you see the multiplexer prism on the left. You see the different colors that we use to depict different signals, but they come at different incident angle to the prism, and they are combined to go through just the optical fiber. At the receiving end, where you have the demultiplexers, the prism also separates the signal back to where they came from. Now, the multiplexing is mainly used as time division basis. So we say in the FDM, frequency division multiplexing, all signals operate at the same time with different frequencies. But in the TDM, all signals operate within the same frequency but at different times. Get it very well. In FDM, we've seen F1, F2, F3 to Fn. In other words, the frequencies are different. But in the TDM, it is only one frequency, but you use them at different times. That is the time division multiplexing. So TDM is a digital multiplexing technique to combine data, but instead of sharing a portion of the bandwidth as in FDM, time is shared. Each connection occupies a portion of time in the link. In TDM systems, an electronic commutator sequentially samples all data sources and combines them to form a composite baseband signal. I've tried to explain what a composite signal is. We will see it clearer now. This composite signal travels through the channel and is demultiplexed into appropriate independent message signals by a corresponding commutator at the receiving end. The TDM operation is as shown in Fig 9. So now, look at basically how TDM works. You see signal 1, signal 2, up to signal 3. They are having the same frequency. They are not the same thing as F1, F2, Fn. They are having the same frequency. So what the commutator does, which is in the multiplex and the mux, is to sample very fast S1, S2, S3 until Sn. Of course, he knows the starting and the ending. When he does that, you group them together and send them as one packet of frame. You see frame 1, he sends that. He samples again S1, S2, S3, picks the data there, puts them in a frame and sends as frame 2. He does it again as frame 3 and continues like that. So we call this type of TDM synchronous TDM because it goes through from one to the last, gets and send. It goes through again from one to the last, gets and send. So say in synchronous TDM, the input is connected to a frame. If there are n number of connections, the frame is divided into n tile slots. One slot is allocated for each input line. In this technique, the sampling rate is common for all signals and hence the same clock input is given. The time slots are transmitted irrespective of whether the source have any data to send or not, thereby leading to the wastage of channel capacity. Although TDM makes use of fixed assignment, however, sources with different data rates can be handled by assigning fewer slots per cycle to the slower input sources than the faster ones. Multiplexing and the multiplexing operation for synchronous TDM is as shown in Fig 10. Let's quickly look at it. Now, this is our Fig 10. The upper is the transmitter, the lower is the receiver. Now, if you look at the upper one, you see frame 1, frame 2, frame 3, frame 4. And when you look at them closely, in frame 3 and 4, you see spaces. But let's see what happens in the synchronous TDM. The transmitter, look at inside the mux, we try to show the arrow, that is the commutator, that it samples them quickly from upper one, which we painted purple. It has 3 data to send. The second one, which is painted green, each of those small blocks are used to represent data. Samples the second one, which is green, the third one, which is blue, and the fourth one, which is brown. So when it goes through them, so it picks one purple, one green, one blue, one brown. It puts them in frame 1 and sends. It goes back, it samples again, it sees another purple, another green, another blue, another brown. It puts them in frame 2 and sends. It goes again, samples, it sees one purple, one green, but there is no blue. It still leaves that space for the blue. And he goes again, he now sees another for brown, he puts it and sends as frame 3. He goes back, he samples, he didn't see any purple. Instead of, he leaves space for it. The second one, he sees a green, he puts it. The third one, he doesn't see any blue, he leaves space. The fourth one, no brown, he leaves space. So you see that frame 1 is filled, frame 2 is filled, frame 3 is not filled because one blue is missing, and frame 4 is only the green that is there. So you see that there is wastage of space in frame 3 and frame 4. So at the receiving end of course, the receiver, it comes there and the commutator sends them back to where they belong. So the output is given as that. Now, we want to take care of these spaces so that they are not wasted. That now gives us leads us to another one, which is now called the asynchronous statistical TDM, otherwise known as the intelligent TDM. What does it do? Let's see. One limitation of synchronous TDM is that many of the time slots in the frames are wasted. This is because if a particular terminal has no data to transmit at a particular instant in time, an empty slot will still be transmitted. The statistical TDM, also known as the intelligent TDM, allocates time slots dynamically based on demand, thereby saving the channel capacity. The MUX scans the input terminals collecting data until the frame is filled and then transmit the frame. As the receiver, the demux receive the frame and distributes the data back to their appropriate terminals. The working difference between synchronous and asynchronous TDM is as shown in figure 11. From the figure, it can be seen that the slots are fully utilized in the asynchronous mode, and the bandwidth of the channel is better utilized. However, since data arrive from and are distributed to I/O lines, unpredictably, address information is necessary to ensure proper delivery. So you can see, for the intelligent one, additional circuitry is needed in order to be able to conserve channel space. Therefore, each slot must have an address path which identifies the source of the data. This type of TDM is used in asynchronous transfer mode networks, which is known as ATM networks, not ATM where you go to withdraw money. There's a type of, communication transmission protocol known as asynchronous transfer mode. If you join me in my next lecture, if you subscribe to the channel and join me in my next lecture, which will be, on understanding the internet technology part 2, we'll be looking at this technology behind the asynchronous transfer mode ATM networks. Now, let's quickly look at this. Please make sure you follow me to understand the time division multiplexing. Now, look at that figure up there. To the right, we have a box which we call high-speed mux, and it has terminals A, B, C, D. Now, if you look at to the left, you see, something like a ladder there, which goes from T0 to T1 to T2 to T3 to T4. And remember what we said, time division multiplexing looks at the same frequency but operates at different times. Now, the high-speed mux has a commutator there which samples the 4 input lines A to D. When it is at A, if you look at the time T0 to T1, there is something which we painted, I can call that still orange. It will see something in A from T0 to T1. It will pick it. Look at frame 1. If you look at, the block below, you see frame 1, 2, 3, 4. If you look at frame 1, when it samples the A terminal, it sees that brownish data from T0 to T1. It labels A1 in frame 1. When it samples again, when it moves to B, T0 to T1 has nothing. It gives an empty space. Then it goes to C. C from T0 to T1 is seeing a green. It puts it C1. D, it gets to D. D from T0 to T1, there is nothing. It gives a dot. It closes the frame and sends. That is synchronous. It comes again. From T1, it goes back to A. From T1 to T2, A has no input. In frame 2, first it drops a space. T1 to T2 in B has a purple data. It puts B1 because that is the first B it is seeing. That is the first B, so it calls it B1. From T1 to T2, it goes to C. There is nothing. It puts empty C. From T1 to T2, it goes to D. It sees the brown slot. That is the first D data is seeing in D. It calls it D1. The four slots are filled for frame 2. It sends it. It does that for frame 3. It goes back to A. Frame 3, which is T2 to T3, it sees something in A. It takes it A2 because that is the second A is seeing. T2 to T3 in B, it sees something. It calls it B2 because that is the second B is seeing. From T2 to T3, it goes to C. It sees something. It calls it C2 because that is the second time it's seeing C. From T2 to T3 in D, nothing. It gives empty space. The 4 slots are filled for frame 3, it sends. It does the same for frame 4. Frame 4, It goes back to A, T3 to T4, A has nothing. It gives empty space. It goes to B, T3 to T4, he sees something in B. That is the third time he sees something in B. He puts it B3. He goes to C, T3 to T4, he sees something in C. That is the third time he sees something in C. He puts it C3. He goes to D. That is the next time he sees something in D. Second time. So that should be D2. Sorry for that. In frame 4, it should be D2 because that is the second data it is seeing in B. I mean, that is the second data it's seeing in D. So instead of that in being D3 in frame 4, it is D2. Now, that is synchronous TDM. Now, see what happens if asynchronous TDM does the same process. It goes to A, that is table the block 2 down. It goes to A. It sees from T0 to T1, it sees a data. It puts it A1. It goes to B. From T0 to T1, it didn't see anything. Instead of putting an empty slot, he leaves that slot. He goes to C. From T0 to T1, he sees something in C. He puts it at C1. He goes to D. There is nothing. Instead of transmitting empty space, he rushes back to A and sees from T1 to T2 in A, there is nothing. He checks again B. From T1 to T2, he sees something in B. He takes it as B1 and puts, say, in frame 1. He goes to C. He checks, there is nothing. Instead of transmitting empty space, it goes to D. At D, he sees something. He calls that B1. So frame 1 is filled now. You see that for frame 1 to be filled, it has gone from T0 to T2. So you see that frame 1 now will be A1, C1, B1, D1. It comes back. By the time it comes back, it's now going from T2 to T3. He sees something in A, he calls it A2. He sees something in B, he calls it B2. He sees something in C, he calls it C2. He didn't see something in D, that is from T2 to T3, nothing in D. So he won't put anything. He goes back, and from T3 to T4, there is nothing in A. He goes to B. From T3 to T4, he sees something in B. He calls it B3 because I have seen B first and second. Then he goes to C. He sees something. He calls it C3. He goes to D. He sees something. He calls it D2 because that is the second time he sees something in D. Now, if you look at the frame in 1, when it is using synchronous TDM, it has used 4 frames. But when it is using the asynchronous or the intelligent TDM, it has used only 2.5. In other words, it has conserved 1.5 spaces if it were to be synchronous TDM. So you see how advantageous it is to use asynchronous TDM. Even though we say it has additional features to be able to determine when it started and when it ended. So now, before we conclude our lectures today, I want you to please look up the following terms: crosstalks, the types and what causes them; intersymbol interference, the types and what causes them; and when we say that signals are orthogonal, what do we mean? So we say what is meant by orthogonality of signals and what is meant by spread spectrum technique. This will be able to, go through in our, coming lectures. You are therefore advised, even if you are not going to be examined on those things because they are not, part of your particular syllabus now. But as somebody that is having substantive interest in communications engineering, it is good for you to, listen when we will do these lectures. And you can only know when we do lectures on all these terms if you subscribe to the channel. So thank you for listening, and we hope that you will join us in our next lectures, and we promise to make it maybe shorter next time. Thank you.